So on behalf of Cecile Henne, our AMWG Science Liaison, and our two external co-chairs and myself, welcome to the summer version of the AMWG. During the summer meeting, we are not as model development centric as we are during the winter meeting, so I just have one slide here. If you need a refresher of what's new in CAM 7 compared to previous versions. As Dave mentioned, we're in the final stages of development. We're only allowed to make changes or major changes in the model if they really reduce biases, and they need to be approved by the SSC. So as far as I'm aware, this is CAM 7. In terms of our shallow convection schemes here at CLUB, we're still using CLUB, but we now have prognostic momentum fluxes in there. We're still using ZM deep convection scheme. There are some changes necessary to deal with high boundary layer resolution. Pumas here is, I could also call it MG free. There has been some updates to how some processes are handled. Last we looked at climate sensitivity. I think it's those changes that reduced climate sensitivity compared to CSM2. Radiative transfer model has been updated, but it's still ROTMG. We're using MAM4 aerosols since we have specified oxidants, but if we one with stratospheric chemistry, it's MAM5 that's active. Then there's been a number of changes in the world of parameterized gravity waves and drag. So in particular, we now have a new source of gravity waves in the model. It really helps some of our biases. After free model versions with the finite volume dynamical core, we've swapped it out with the spectral element dynamical core. We've increased the boundary layer resolution, and also we have now raised the lid. So for a couple of decades, the top has been around 42 kilometers. Now we have an 80 kilometer top. Horizontal resolution still stuck at 1 degree, but we also would like to develop a high resolution version of CESM at a quarter degree as well. And then in the other components, major change, the ocean changed to MOM6. Luckily, Dave showed a lot of these slides here because my slot is only 6 minutes. I'm just going to show one science result here. This is the zonal mean wind in the 80 kilometer model. And as Martina has plotted here, our wind biases in the southern hemisphere here compared to ERA 5 look really, really good. There's still some work to do with the northern hemisphere jets. Dave showed this slide with the QBO, so I'll skip over it. He also showed this slide from Adam Harrington on the Greenland mass balance. But I would like to highlight this. So we spent a lot of core hours before AGU last year running quarter degree simulations, and we would like to make the community aware that this data is available. So we ran the high top and the low top version, also reverted to the CAM 5 vertical grids. We experimented with the CLUB momentum fluxes and also did plus 4K SST experiments. Dave showed the results from some of these simulations earlier today, but if you would like to dig into this humongous data set, please follow that link up there and or contact Cecile. Alrighty, the way we've chosen to lay out this meeting here is to give everybody an oral slot. So if you take 90 minutes divided by the number of participants, you got approximately 12-minute slots. So speakers have 10 minutes and then 2 minutes for questions. Please notice we need to finish on time because we have the group photo here at 3 p.m., so during the break. And in the interest of time, let me switch to the next speaker. And not take questions. You can grab me in the break if you want to chat about something. But our first speaker here is Vince Larson. He's going to talk about the use of tuning diagnostics to understand CAM's behavior.
Yeah, great. Well, thank you so much for giving me an opportunity to talk. My collaborators on this are Ben Stevens, Jun Guo, and Luis Hasenauer. It all started innocently enough. We wanted to reduce precipitable water, which is TMQ in CAM's parlance. And so we shut off Club's background diffusion. So Club's background diffusion, it's sort of a historical artifact at this point. It was introduced many years ago in order to improve marine stratocumulus, but it doesn't really do that anymore. And so it's sort of an ugly wart that I would like to get rid of in the model. And it has a side benefit: if we shut it off, it reduces TMQ and improves it. So if we run default cam, this is model minus obs here, we see that it has a moist bias, a pretty strong 1.39. If we shut off Club's background diffusion, which just is lofting up moisture and heat using a simple eddy diffusivity while Club's higher order closure moments are going on, then the moisture bias is reduced to 0.22, which is good, but it leaves this dry patch here in the Western Pacific and in the Indian Ocean, which is bad. So we decided to retune using a semi-automated tuner called QuadTune, and that helped, but biases still remain. So this is where we were with this dry bias here, and then this is where we end up after tuning. The dry bias in the Indian Ocean is reduced to some extent, but the dry bias over the Eastern Pacific is actually made worse. So why doesn't tuning parameter values remove these model biases? It feels like parts of the model structure must be preventing further improvement. There's just a model structural error. And the question is, can we get at some hints about where those model structural errors lie by exploring the tuning trade-offs? Okay, so in the remainder of the talk, I'll talk first about tuning trade-offs in cloud brightness, in other words, shortwave cloud forcing, and then I'll talk about tuning trade-offs in surface precipitation, aka PREC-T. Okay, so after tuning, the shortwave cloud forcing improves, in other words, the clouds dim in the southern hemisphere storm track. So this is where we were when we had shut off the background diffusion, but before tuning. And you can see here on the southern hemisphere storm track in this yellow box, there's a very bright region. It's so bright it goes off the scale there. But after tuning, then it dims somewhat, which is good. Likewise, in this pink region off the coast of Japan, it has this ugly brown shade here, which after tuning is turned into a much more pleasing taupe color, which means it's dimmed as we want. But the problem is here. So over here in the Peru stratocumulus region, it looked fine before tuning, but retuning makes it too dry. So then the question is QuadTune, this automatic tuner, sacrificing this stratocumulus region in order to improve the storm track or the coast of Japan? And it's kind of hard to tell looking at this. Both of them are too bright. They both get dimmer, so it's not clear what the tension is. But we did some experiments. These involved basically finding many sets of parameter values, each of which produces a good climate. So it's sort of a calibrated physics ensemble. Each scatter point corresponds to one parameter set. And then we just looked at how these behaved in these two regions, off the coast of Japan and off Peru. And we want all the points to lie on this green triangle of no bias, which would mean that we can fit both regions. And in fact, we do find some points that are pretty good fits. So that's good. It doesn't seem like there's a trade-off between Japan and Peru here. But with the storm track, it's a different situation. Here we want at least one parameter set to land on no bias, but in fact there's this trade-off. We can either fit Peru or we can fit the storm track, but there's no single parameter set that matches both regions. So it feels like there's some basically model error involving those two regions. So why is that? We can get some insight by looking at this chart of biases in different regions. So what we see is in the storm track, there's a very strong bright bias to begin with. That's the vertical black bar. And in Peru, there's less of a bright bias, but it's still a bright bias. But after tuning, then the clouds are dimmed and brought closer to zero, where we want them for the storm track, and that's the end of this horizontal bar. But then, unfortunately, Peru is over-dimmed. It becomes too dim. And we can look at how the parameters are achieving this dimming. There's a parameter C1, never mind what that is, but it brightens Peru, it brightens the storm track. We have C8, that dims both. We have C14, that dims both. The parameter dependencies are very similar. So red, red, blue, blue, green, green, and so on. So you can kind of see that it's sort of hopeless to bring the storm track down to the proper brightness without over-dimming Peru. And this surprised me, frankly, a little bit, because I think of storm track clouds as being very different than marine stratocumulus clouds, and I was expecting to find a parameter that could regionally tune the storm tracks, but I haven't found it yet, even though Adam has given me lots of helpful hints about microphysical parameters and ZM parameters. So I'll keep working on it, but this is sort of the state. Now, off Japan, it's quite different because the parameter sensitivities are different. This blue is different than that blue. This lime is different than that lime. So we have some hope of tuning them independently, and in fact, we do. Okay, so now if we look at the precip biases, the precip has sort of a similar trade-off between the Indian Ocean and this Eastern Pacific ITCZ region in purple here. So the Indian Ocean, this is before tuning, starts off with not enough rain, but then after tuning, it's mitigated to some extent. The Eastern Pacific ITCZ starts off fine before tuning. After tuning, it has too much rain. So it sounds like the similar sort of bias that we were seeing before, where the initial biases are very different. We tune up the rain everywhere, and then that makes one region better and the other region worse. Okay, but what's interesting here is the Indian Ocean here is too dry. Off the coast of Japan, it's too rainy, and both those biases improve. So that's a very different situation. Something different is going on there. We can look at that, and we can see, okay, Indian Ocean and Eastern Pacific ITCZ, they have this sort of trade-off. We'd like them to be here, but we don't have a single point that does that. For off Japan and Indian Ocean, it's very different. If you improve one region, the rain in one region, you improve the rain in the other region, which is very nice. That's quite handy. Why is that? Well, we notice here that the Indian Ocean, it's too dry to begin with. It becomes moister through tuning, more rainy. Off Japan starts off too rainy and becomes drier, which is beautiful. And these parameter values, they have a remarkable similarity, but with the opposite sign. So this pink is like that pink, this lime is like that lime, pink is like that pink, and so on. And what seems to be happening, so the very same parameter that makes Indian Ocean more rainy makes off Japan drier. And what seems to be happening is basically the vertical velocity is very tied up in this. There's an amazing correspondence between surface precip and vertical velocity in these particular runs. And the circulation is changing so that basically we're getting more ascent in the Indian Ocean and more subsidence in the coast off Japan, which is just what we want. And so then that's what seems to be helping us here. But there's still a problem with the Eastern Pacific ITCZ. It seems a little strange that, for instance, this Cape limit parameter, it both boosts the precip in Indian Ocean and ITCZ. So I'm not quite sure why that's happening, but again, we're working on it. So conclusions are, if we tune, we can dim the storm tracks, but in so doing, we dim the Peruvian stratocumulus too much. So we need a parameter that's more specific to the storm tracks. But in the process, we learned something about the physics, namely that the clouds in the storm track and in the marine stratocumulus regions respond remarkably similarly to each other, which was surprising to me. But then also we learned that tuning is very much complicated by circulation changes. And then we also need to deal with the Eastern Pacific ITCZ. So yeah, thanks for your attention. Okay. Thank you. Try again, can I?
Oops. Hi, very nice talk. I'm a grad student, Papu Paul, from University of Illinois. My thing is like, as you are tuning, it improves one region and it degrades other region. So why not we are trying to make the like localized parameter for different region, like the MPAS model, where we uh, increase the resolution in one region to improve the model performance. Why we are not doing the same kind of thing for parameter tuning to make the parameter for regional? Yeah, this is the parameter set for Eastern Pacific. This is the parameter set for Western Pacific, and so on and so forth.
Yeah, it's a good question. I mean, we want to keep the model simple. And then in addition, the hope, we don't want to sort of bake in a certain change in a certain region, and maybe in a different climate, that region has shifted, or, so we don't want to force the answer too much. But we do have some parameters that are specific to land or ocean, so.
Thank you.
So you alluded to this a little bit about what do you think about the hypothesis that if you want to make a differential change one region, like more precip in one region, less precip in another region, that you want to change the circulation through your parameter tunings. But if you want to, or if you do manage to just tune, like if you're just changing cloud parameters, like you're probably going to affect clouds the same way everywhere. Is that what you've seen?
Yeah, so that's what I see. So basically, when we want to tune the clouds, the parameters basically dim or brighten globally. So if we start with clouds that are too bright here, too dim there, we don't really change things. With the precip, it changes. Precip is more constrained, right? So if you have more precip here, you sort of have to have less there in an F-case type run. But it still was interesting to me exactly where the circulation changed, like over the Eastern Pacific, that apparently we didn't have the same subsidence that we enjoyed off the coast of Japan. So there's a somewhat local circulation, which is helping us in one place but not another.
Great, thanks.
Thanks.
Thank you, Vince. Next up is Ben Stevens, who is going to talk about cyclones and quarter-degree simulations.
Thank you. This is kind of an expanded version of a talk I gave at the AMWG winter meeting earlier this year, with some updates about some tuning we've done. I want to especially acknowledge Julio and Colin, because my experience is mostly with club at 1 degree, so cyclones at quarter degree is basically all new to me. So I'll bear with me as I try to convince you that we're doing better now than with Cam 7 than we were with Cam 6. So Cam 5 and Cam 6 both used a down gradient scheme for the momentum fluxes. As part of the work that I've been doing with the momentum CPT, we've now incorporated prognostic momentum fluxes into Cam 7, and you can see the equation for that here on the right. It's the full prognostic equation that you would get from the Reynolds stress tensor, with terms that are closed using Club's PDF, and other terms that are closed using standard pressure closures. So as far as the large scale characteristics of what we're seeing in these quarter degree runs, and these, by the way, are fully quarter degree runs, they're not regionally refined. A couple of things I'll highlight are just, there's too many cyclones. It turns out there's too many after an analysis by Collins, Zarzicki. But we do think that the prognostic momentum looks better in the East Atlantic than the diagnostic case over here. I know this is a text-heavy slide, but I wanted to give Collins takeaways because he knows more than I do. But basically, it looks like we're doing better even than Cam 5 in some ways, and even with the diagnostic momentum flux version of Club. but the prognostic momentum flux improves on that a little bit in some cases. So one of the things that, in particular, that he pointed out was that one of the challenges is that there's just too many tropical cyclones, about 2 times what the obs would show. And so we were interested in seeing if we could maybe improve that somehow. And that's sort of what this last comment is about. But hopefully those of you who are familiar with tropical cyclones can take a little bit away from this slide. So let me move on. So these are some more recent runs that we've done now. The one on the left here is still a fully quarter-degree run, but it's now done with the ZM tau parameter reduced from 3600 to 1200. This is intended to reduce the number of tropical cyclones, and it does. It reduces the number of tropical cyclones by about 40% or so. And the numbers, if you look at them, are actually pretty close to OBS at this point when we reduce that parameter. And I just thought I would include this plot on the left since we started doing, I think this was the last of the fully quarter-degree runs we did. We started doing regionally refined runs, but this is sort of the corresponding case on the regionally refined side. Okay, so before, when we were just playing with the diagnostic versus prognostic momentum flux, I took a look at some of the smaller scale storm structure, in particular inflow angles and inflow depths is one of the things I looked at. And we do see an improvement using prognostic momentum flux. So you can see that the inflow angle increases by a few degrees in both the Northwest Pacific and the North Atlantic. And then there's a corresponding decrease in the inflow depth. So this is looking good. Although observationally the inflow angles are higher. I think observationally they're maybe in the low 20 degrees. Although Colin has said that for quarter-degree simulations we might aim for something more like 17 or 18 degrees. And so actually we are able to get a handle on that using one club parameter in particular called CUU shear. When we increase that parameter, it basically reduces turbulent production in the horizontal momentum flux equation. So we expect to see maybe a shallower boundary layer in that case, and that seems to correspond as well to an increased inflow angle in both basins again, and again with reduced inflow depths. So it's nice to know that we're able to get a handle on this using just a single parameter and get numbers that we like a little better. These are some plots that show composites of storms in the different basins. This is for diagnostic momentum flux. So what we notice here basically is that the prognostic looks a little better. The winds are sort of pushed, or the radial winds are kind of lower down in the column as where we would prefer them to be. And it's the same situation roughly in the Northwest Pacific. This is again just diagnostic versus prognostic momentum flux. So we see that feature where the winds are, the radial winds are lower. With some tuning, with using the reduced value of ZM tau and the increased value of CUU shear, I think we see that we're getting a little bit of a further reduction in the height of those radial winds. There is a caveat here. I wasn't able to use some of my latest results on the right-hand column here. I ran this experiment out for longer, which might, I think, improve the statistics, especially in the North Atlantic, where I think the N value is maybe a little small. But because of the computers being down, I wasn't able to get to that just before the talk. This is one of the last plots. So this is thanks to Colin Zarzicki. He created this plot. I noted what the colors correspond to here in the text, but basically blue is OBS. Red is where we were with CAM 5. This is the pressure wind plot, by the way. CAM 6 showed a degradation in this metric. That's down here with green. If you look at the diagnostic versus prognostic cases in our updated version of CAM, they're kind of right on top of each other. It's the orange line and the purple line. If you can kind of see them, they actually are on top of each other out here, but you can sort of see them separated over here. So there's not much benefit, I guess, from turning on the prognostic momentum flux for this particular metric, but we do see improvements in other ways. Tuning CUU shear and ZM tau gets you this yellow line, which is a slight improvement on the high wind speed end. So yeah, basically the momentum CPT has made prognostic momentum flux the default in Chem 7. 2 preliminary 10-year runs by Cecile show a number of improved results when using the prognostic momentum flux versus diagnostic. We've learned that overproduction of TCs can be mitigated by reducing that ZM tau parameter. Prognostic momentum flux shows better results for inflow angle and depth. We also see improvements in the composite storm structure using prognostic momentum flux. Pressure-rend relationships, there's still room for improvement there if we can maybe get a better handle on it with some tuning maybe. And then finally, yeah, tuning also further improves the inflow angle and inflow depth, yeah, with that club parameter. So that's kind of where I am currently with the tropical cyclone stuff at quarter degree. Thank you.
You remind me of the improvements that we see with the prognostic momentum fluxes. You said you weren't seeing in the wind pressure relationship. Where else?
Oh,
Yeah.
well, in the storm tracks we see it looks better in the East Atlantic, I think. There were, I think, maybe too many tracks over that region for the diagnostic, but the prognostic looks better compared to OBS. Also, the inflow angle and inflow depth look better with the prognostic momentum flux, and the composite, the contour plots that are averaging over many storms look better. The radial winds are closer to the surface, which I think is what we, as I understand it, that's what we like.
Staying on schedule. So my colleague here, this is not João Teixeira, this is Adam Harrington. He's going to give a presentation on the Club MF project.
Yeah, so thanks everybody. I'm going to talk about the Club MF approach, results from the Unified Mixing Parameterization CPT project. So the Club MF is just one leg of that project. João Teixeira is the PI, and yeah, unfortunately he wasn't able to make it here today, so I'll be giving this talk for him. The NCAR PI is Julio Backmeister, my advisor, and Xianan Jiang also contributes to Club MF. He's at UCLA. So we'll get started by stating, which should be obvious to a lot of us, that convection occurs over an extremely large range of scales in the atmosphere. This schematic here is showing, starting over here in the region of the eastern boundary currents, you have a colder ocean with a stratocumulus top boundary layer. As you progress towards the tropics, the SST is warm and you end up with a shallow cumulus transition. As you go further down into the equator region, you end up with your trade cumulus, mid-level convection, and all the way to your ITCZ where you have deep convective anvils. And so we seek to try to parameterize these transition of different convective regimes in some way of a unified way. There's also the temporal transitions in convection over land. This is the diurnal cycle problem that a lot of GCMs struggle with, where the convection sort of shoots off too early in the day. And so we seek to improve that aspect. And in particular, current GCMs usually parameterize these different convective regimes using different schemes. And so you'll have your PBL scheme down here in the yellow. That's the wrong button. Down here in the yellow, so that's just doing your PBL mixing, and usually is actually pretty effective at producing stratocumulus clouds. Your shallow convection scheme is going to be doing the shallow cumulus, and your deep convection scheme is going to be doing your deepest convection. I have these boxes overlapping over convective regime because it's, not all schemes have explicit separation between convective regimes, and things like mid-level convection might be partially represented by the deep convection scheme. The shallow convection scheme might try to take a crack at it. Some of this sort of depends on actually how you do your time splitting and the physics loops. So you could be a little smarter in your process ordering to prevent this sort of overlap behavior, but it is a bit of a side effect of this approach. And so to unify these convective regimes, we're going to start with the eddy diffusivity mass flux approach model. And so it's a convection scheme that computes the turbulent fluxes from convection into a down gradient diffusion scheme that would do your small scale turbulence, and then a mass flux plume model, which will handle your cumulus convection. And so the actual mass flux plume model that we'll be using in Club MF has an explicit ensemble of plumes that we initialize by constructing a PDF of the subgrid vertical velocities in a grid box, and initialize our plumes from there. We compute the lateral entrainment, and each one of these, this must have been converted to PowerPoint or something. All my formatting is a little different. That's okay. This is the fractional entrainment rate that each plume ensemble feels, and it's stochastic, and that's given by this squiggly P, which is referring to a Poisson distribution with a mean of the layer thickness over L, which is our entrainment length scale. So the entrainment length scale is defined here as the vertical distance a parcel undergoes before experiencing a single entrainment event. And so this squiggly P will return the discrete number of entrainment events that have occurred over the layer delta Z. And then you can we integrate a steady state updraft equation vertically with these entrainment rates and the buoyancy. So there's no convective quasi-equilibrium assumptions in this scheme. And the way that we will try to parameterize different regimes is by varying this entrainment length scale. And so we want this dynamic in time and space, where a small entrainment length scale would be shallow convection, a large entrainment scale would be deep convection, and mid would be in between. Yeah, this is a bit problematic. So I will just state what's underneath the figure here. With Club MF, what we did is we swapped out the eddy diffusivity term with Club. So Club, as Vince just talked about and Ben talked about, cloud layers unified by binormals. It is a prognostic turbulence scheme, and it closes the higher order moments in the prognostic equations using an assumed distribution method. That assumed distribution method is a two trivariate normals. And then what we do is we couple these mass flux plumes to the club solver in the 5-diagonal club matrix that solves for the prognostic fluxes. And so the Club MF equations look like this, where the club solver will spit out the total fluxes due to mass flux plumes and prognostic turbulence. So there's 3 different versions of Club MF of varying complexity. We started with the just one that targeted shallow convection, and that's for, we set this entrainment length scale to something fixed that you just set as a nameless parameter. It produces a pretty nice result. So this is a single column model simulation of the shallow cumulus Bomix case. The And it's a grid point in space and time, and so what is shown here is the subgrid distribution of liquid water potential temperature on the x-axis and total water on the y-axis. The faint PDF lines here are the PDF you get from an LES model, so we ran an LES model to be our truth. The club joint PDF is this darker oblate shape here, and you can see, so it's quite a bit narrower than the PDF produced by the LES solution. And so the mass flux plume, this is the explicit ensemble of mass flux plumes, so I think there's 100 plumes in here. And as you can see, they kind of fill out this skewed tail of the PDF that isn't being represented by club's joint PDF. So then we extended to deep by coming up with an entrainment length scale formulation as a function of the environment. And the latest, greatest version I call Club MF Arrow down here. And here the entrainment length scale is a function of plume history properties. We also have an explicit downdraft ensemble. And that actually allowed us to make a cold pool feedback on the entrainment length scale. And these three bullets here kind of give us this diurnal cycle over land that we've really been targeting. And so this is a single column model in the LBA case, which is convection over land. And this is the top of the plume ensemble. The dashed black lines is the LES solution, and the red is our latest, greatest Club MF version. So it does a pretty good job, and it has, the precipitation rates are just as predicted by the LES. So now moving into 3D model simulations. So this is a 20-year AMIP simulation. And what is shown here is a PDF of the precipitation rates in the tropics. The black line is the iMerge observational data product. The blue and cyan are CAM6 and CAM7 respectively. And the yellow here is Club MF. And so this drizzle problem that gets expressed in CAM6 and CAM7 is shown as where the line is more probable than observations for rain rates of about 10 millimeter per day or less. And Club MF seems to improve that quite a bit. It also produces more extreme precipitation events that you don't get for CAM6 and CAM7. Another look at convection in the tropics in the simulations. These are Havmauler plots. The left column is this GPM DPR data set that's not globally continuous, so there are extrapolated values under the regions where it's shaded. The top row is the convective precipitation rate. The middle row is the stratiform precipitation rate. And so GPM DPR actually has these components broken down using this bright band proxy for what they consider stratiform rain in the observations. And so we utilize those to provide the ratio of the convective precipitation over total precipitation. And so the values are usually around 50% on average in the observations. In CAM6 and CAM7, it's about 80 or 90% convective precipitation rate occurring in the tropics. And Club MF, which we were really happy about, was able to bring that down to closer to 50%, more in line with the observations. Now I want to talk about the latest, greatest version of Club MF, and I was able to, again, this is missing an attribution here, but I work on CEMA. CEMA is developing kilometer scale capabilities in CSM along with help from Earthworks and the CSM project. So we were running these 3.75 kilometer simulations. The cloud field in the Western Pacific looked like this in that solution. Mind you, the only convection scheme active is Club. We've turned off deep convection. And what you have is all these sort of sprinkles of deep convection occurring over almost everywhere and very intermittent. It's just like a mosaic of deep convection occurring everywhere. And so what I think is going on here, and I certainly didn't come up with this myself, but these 3 kilometer models, they can support these 10 kilometer updrafts, 10 kilometer wide updrafts. However, the entrainment rate responsible for mixing that updraft for the environment, those are from order 100 meter eddies. So they're not resolved. and they still need to be parameterized, and they're not really explicitly parameterized in these models, except that the diacore has scale selective numerical filters. In this case, MPAS uses a Smagoriski scheme, which is doing a little bit of mixing, but it's not parameterizing the entrainment process correctly. And so basically the only convection this model can support is like a very deep undilute mode with a high level of neutral buoyancy. And it kind of just does that everywhere. We think you need to have some type of parameterized convection to handle these transitional cumulus regimes. And so this bottom panel is a rerun of the simulation with ClubMF. And you can see our sprinkling of deep convection problem has for the most part gone away, and we have much more organized structures coming about. And this also manifests in a better skill score. So this is a Diamond 1 simulation that's initialized from ERA5 on August 1st, 2016. So the first several days of that simulation you can consider initialized prediction. And so the RMSE for CESM out of the box is the gold, and the red is with ClubMF. And so we brought our RMSEs, with respect to precipitation in the iMerge data set down significantly. This is the MQ Diamond 1 simulation, so we're not quite as good as them yet. We plan to spend the next several months sort of calibrating this configuration a little bit more to bring down our RMSEs, playing with what in ClubMF is helping a lot and what is maybe not helping. Essentially, really hone in on an optimized version of the kilometer scale configuration with ClubMF. So that is everything. And so I'll take any questions you guys have.
Move on because we're out of time. Well, if my boss has a question, I can't go against it, I guess.
Is there a danger in using RMSE as a score that you're just going to drive yourself to smoother fields, basically? So it was smoother, which it possibly wants to be, but even smoother still will probably continue to improve the RMSE. So you might want to think of another way of analyzing it, to perhaps cloud scale structures or something to get a bit more confidence.
Yeah, okay, will do. Thanks. I would imagine pattern correlations would have the same problem where you get
Okay, thanks, Adam. Next up is an online presentation by Brandon Duran. He's going to talk about aerosol effects in the ice clouds in a CAM6 perturb parameter ensemble. Away.
Yeah, thanks. Thanks to the organizers. Sorry I couldn't be there in person, but excited to talk a little bit about a high cloud response to aerosols in a perturbed parameter ensemble. I want to thank my co-authors, and then also want to thank Brian, Truda, and Christina and Kar, who have kind of helped through the process of this. So I'll jump right in, give a little brief overview of the PPE that we're looking at. So we're running this PPE with the version of CAM 6.3. If you're familiar with the PPE that was ran a couple years ago by Truda and a few other folks, it's pretty similar to that, except that we've really reduced the amount of parameters that we're looking at. So we only look at 19 parameters, focusing strictly on aerosols and microphysics, but we essentially inherit most of the parameter ranges themselves from that original CAM6 PPE. And we run a set of 162 different simulations across a variety of these parameter perturbations. And so to give a little more detail about what we're thinking about, we're really focusing on aerosol forcing. So we have kind of two different types of simulations that we're looking at. Each are run for 2 years long with fixed SST. So we have a pre-industrial and a present day run. And the two of them only differ in the aerosol emissions that we prescribe. So in the pre-industrial run, we're looking at 1850s aerosol emissions, whereas in the present day, we're looking at 2010. And then these are nudged runs, so we're nudging horizontal winds above the boundary layer. And I just show these two kind of basic zonal mean plots for our ensemble, just to give a sense of what's going on. And so essentially just what to take away from this is the green curve, which is showing the present day simulations,
you can see on the right this kind of strong increase in the northern hemisphere in the vertically integrated droplet number concentration. So that's really just highlighting the aerosol forcing that we're going to take a look at. And then to kind of just orient ourselves, there's kind of a few methods that are usually used for diagnosing aerosol forcing. Given how short this talk is, I won't really go into them, but typically a lot of people use this GON method, which is just uses aerosol-free radiative fluxes from the model, and then APRP is another kind of common method that's used. But actually, in our talk, or in this talk, and then kind of in the results that I'll show, I'll kind of focus on this method on the right, which is this new cloud radiative kernel method that we've developed quite recently that relies on satellite simulator output from the models. And really, the reason we hone in on this is because we're able to kind of separate the contributions from liquid and ice cloud changes, which can kind of allow us to get a deeper sense of what's going on with aerosol forcing. So I'll just kind of briefly touch on what this method is, just to kind of give you guys a sense of how this works. But essentially, there's two components to this method that, so on the left, what we're looking at is GCM output from the MODIS satellite simulator. And so what you're looking at is just an example of the change in global mean ice cloud fraction. And the nice part about this simulator output is that it's showing cloud fraction according to two kind of key cloud properties, in this case, effective radius and ice water path. And so we're able to not only see changes in the total amount of clouds, but also in the properties of the clouds themselves, which are radiatively quite important. And then the other component of this method is this cloud radiative kernel, which is generated offline using a radiative transfer model. And so you can really just think of this as dTOA over d cloud fraction, so measuring the effects of changes in cloud to the radiative fluxes. And just on the right, this is kind of showing basically that as you move from the bottom to the top, you're moving to clouds with more cloud water, which are thicker clouds, which reflect more incoming shortwave radiation. And then as you move from right to left on this plot, you're moving from bigger ice crystals to smaller ice crystals. So you're increasing the surface area and the albedo, enhancing the reflectivity. So that's a kind of very brief overview of this method. And I'll just kind of jump right into the results here. So this is the ensemble mean shortwave ERF ACI for just ice clouds. And I really just want to draw attention to the top left plot of this kind of figure, looking at the total aerosol forcing from ice clouds. And so what I really want to point out here that's interesting to us is that the ice cloud response is quite heterogeneous. And so you can see there's kind of this dipole of warming in the tropics and then this cooling over Asia and its outflow region. And this is quite interesting because it's really in contrast to what we see with liquid clouds. And so what I'm showing here is just the ensemble mean changes on liquid and ice cloud fraction from the MODIS simulator. And what you can see is that with the addition of aerosols on the left here, liquid clouds tend to increase almost everywhere across the globe with a few small exceptions. Whereas on the right here, the ice cloud fraction kind of has this heterogeneous pattern. So this is really interesting and something that we want to try to understand better in this PPE. And then I just show here that no matter what method of kind of diagnosing aerosol forcing, this warming effect in the tropics is observed. So we kind of want to dive into understanding this, and everything that I'll share from here on is pretty preliminary, so we're still kind of trying to unpack what's going on. So what I'm showing here are longitude and pressure plots over kind of the tropical Pacific, 10 south to 10 north. And just to kind of orient the picture here, on the left, we're seeing the pre-industrial control cloud in the model, and then on the right, we're looking at the change in cloud. And so you can see that this warming effect that's happening in the tropics is largely coming from this pretty strong reduction of high clouds over the kind of western and central Pacific. And so kind of to try to understand what's happening here, I'll walk through a few other plots. So on the left, you're looking at the change in cloud ice number over this same region. And you can see there's kind of this strong decrease in the tropics, in the upper atmosphere. And on the right here, I'm showing the change in the activated ice number from homogeneous nucleation. And what you can see is really that reduction in cloud and cloud ice number that we're kind of observing in this upper layer of the tropics could probably be coming from this strong reduction in homogeneous nucleation. And there's potentially a cool story here, which is that the same plot on the left that I just showed you, which is this decrease in homogeneous nucleation, is kind of, there's this corollary increase in heterogeneous nucleation in this upper region of the tropics. And despite the fact that kind of the magnitude of these changes is quite different, this could be an indicator that there's maybe this increased competition where heterogeneous nucleation is occurring at kind of lower supersaturations and really suppressing the homogeneous nucleation. But that's kind of a pretty early story that we have here, and we really need to do kind of more testing to try to unpack whether it's the microphysics here that's really driving this, or whether there might be some macrophysical changes potentially related to kind of changes in the transport of the vertical transport of water vapor that's getting up to this upper layer of the atmosphere. So that's kind of all we have here. Definitely an ongoing work in progress. Hopefully we can get some ideas moving forward. And I'll kind of just leave these conclusions up on the screen. And yeah, hopefully there's some time for a few questions.
Right, doesn't look like we have any questions, and it's just been brought to my attention that Trude canceled her talk, so we actually have plenty of time here before the break. So let's thank Brandon again. And the next talk is also remote from Norway, so thank you for staying up late. It's Ada
Thank you,
Jamundsen.
April.
Ada Jamundsen is going to talk about the impact of model resolution on climate in the Norwegian version of CESM, so NOR-CESM, ESM.
Thank you, and thank you for letting me present. Do you hear me?
Yes.
Yes, good. Okay, so my name is Ada Gjermundsen, so I'm an associate professor at the University of Oslo and also a researcher at MET Norway. And I'm in the coordination team for the model development of NORSM. So I'll show some first results today, and we are still very much developing the model, but yeah. So just short, what is NORSM? So it's been developed since 2008. It's a consortium effort, so we have 7 Norwegian institutes contributing. So it's not one partner responsible. We're doing this jointly. We contributed to CMIP 5 and CMIP 6. We have more than 60 national developers, and NORSM is used in more than 50 research projects every year. So on Norwegian scales, that's pretty good. We are currently developing NORSM 3 for CMIP 7, a model resolution similar to CSM 3. And we plan to freeze the model development on the 15th of June. At least have a chill. Just to show you, so we share a lot of components, or it's a lot, in large part based on CSM. So here I show in blue some boxes which are the CSM-based components, like CAM, CLM, Mozart, and CICE, or size. But then we have some unique components, like the ocean component is unique to NORSM, and also the ocean biogeochemistry. And we have a different aerosol module with aerosol physics and chemistry, and also how aerosols interact with radiation and clouds are different in NORSM compared to CSM. Also, we use CLM, the land model with dynamic vegetation and fates. So the development and fates and also the land ice system that's done jointly with NCAR. So in large part, a lot of similarities, but we also have some differences. So if you compare the CMIP 6 versions, so CSM2 and NORDSM2, so this figure was shown by Dave earlier this morning. So you see it's based on this is from the Fasullo paper. So it shows performance for the CMIP 6 models on pattern correlation, and different radiation and heat variables. And we see that CSM2 was ranked top, but then NORDSM2 with similar resolution as CSM was also ranked high, which is maybe not so surprising given the similarities. But if you look at the climate sensitivity, there are differences. So CSM2 was ranked or was among the highest climate sensitivity models in the CMIP6 ensemble, while NORDSM2 was among the lowest with a climate sensitivity of 2.5 for both the 1 degree resolution model and the 2 degree resolution model. Just some experience from the CMIP 6 versions of NORDSM. So we had 2 versions, a core resolution version with 2 degree horizontal resolution for atmosphere and land, and 1 degree for ocean and sea ice. And then we had a medium resolution, which was a resolution similar to CSM2, so that's 1 degree horizontal resolution for most components. What we found was that even if the coarse resolution performed worse when it comes to patterns and pattern correlation and precipitation patterns, for instance, when we consider the climate feedbacks and also the forcing, the 2 model versions performed very similar. So here you see, for instance, the feedbacks from a 4 times CO2 simulation. And black is the coarse resolution and orange is the medium resolution, and you don't see the black circles because the orange circles are above because they have the same values. We also saw that this is showing the top of the atmosphere radiative imbalance for the 1 degree resolution in solid and a 2 degree in dashed. Also very similar. So what we ended up with was to use the coarse resolution model version for a lot of the CMIP 6 production runs. Not all, but a lot, because it's so much faster and also lower computational costs. And it's also used extensively at the universities because of that. So now we want to have a 2 degree horizontal resolution also for NORDSM3. So we are using CAM7. So the main motivation is then to develop a faster and more cost-efficient version of NORDSM3 based on the 1 degree configuration. So we want it as similar as possible. We also we aim then to tune the 1 degree resolution version of NORDSM using results from the 2 degree resolution. So CAM7 in NORDSM, what we used is in large part what is developed at NCAR. We have some differences, the aerosols, which I mentioned. We also had a modified atmosphere ocean flux calculation. We used the ocean flux scheme 1, which is the core parameterization scheme. We have a different secondary ice scheme, and also the coupling to the ocean is different, and aerosol emissions, or DMS, for instance, because we have a different ocean model. So we're using this NE16PG3 grid for atmosphere and land. Then we have a different mask for the ocean. And we're using the same files and setting as CSM for topography and spectral element core, dry deposition, and so on. So this is the tag, the CAM64085 tag. When we start running it, just not changing anything, having it exactly the same file names and name lists and parameter values as as the 1 degree version. We show here the surface air temperature for the 2 degree and the 1 degree and the difference. And we see that the 2 degree is warmer almost everywhere except over Antarctica. And this was the same that we saw in the CMIP 6 version, that the 2 degree is much warmer. For precipitation, we get a more pronounced double ITC set, which was not maybe so unexpected, but not maybe so desired either. And also we have a drier Amazon compared to the 1 degree version. If we just look at some globally average time series, we see that the 2 degree version, it exhibits a more positive top of the atmosphere imbalance. It's warmer at the surface. It also continues to warm. It has similar short wave cloud forcing and similar drift in the sea surface salinity as in the 1 degree version. But the long wave cloud forcing is more positive, which is also, it's too positive already in the 1 degree version. So that was not so desired either. So what we have done now is, this is more like a test of a method than, so it's like a mini PPE. We will expand this in the future, but we tested first with just 4 parameters at 25 members. And we want to do this in coupled configuration, because what the experience for CMIP 6 was that we did a lot of like PPE work on atmosphere and land, and then we coupled it with the ocean, and then everything was different than how it looked in just atmosphere and land alone. So we want to do this in fully coupled configuration, but then using the 2 degree version. So this is just a start with 4 parameters, 2 from the microphysics, 1 from the convection, and then 1 club parameter. Yeah, so we so member 1 is the reference, which is identical in the setup as the 1 degree version. And then we have all the members below that, and this is a very intense color scheme. I'm sorry about that, but we have then ranked them with this normalized RMSE. And we want to find members which not all need to be ranked like top, but they need to span the whole range of model behavior. So we want members which are not showing like similar, if it's doing very well on precipitation, for instance, it's good if it's not doing as well as the one we're comparing to. So they kind of rank differently from the different variables. But from this, we picked 4 members, which we continued. So here you see the same time series. And then this is the time where we branched off and with these 25 members in this mini PPE. And then we continued after that 4 members to try to find out how it behaves on the on longer timescales, since this is a coupled configuration. So we see that with only these 4 parameters, we span already a large range of values, and yeah, and they don't all behave the same. So we will continue then a subset of these members and then investigate the long-term behavior of the model to see then if you can use this. But we will do it a bit more, use more parameters to tune for the PPE in the future, where we have actually freeze the model development. But then we'll see if we can use this as a method for tuning the 1 degree version. So we need to further investigate if this 2 degree version of NORAD-SAM 3 exhibits similar forcing and feedbacks as the 1 degree version, as we found in or saw for the CMIP 6 model version, but that's not necessarily applicable to the CMIP 7 version. And then we hope to tune the CMIP 7 version at 1 degree resolution using the results from this 2 degree version. PPE in a coupled mode. And we also aim to streamline the workflow, so building, running, and analyzing the PPE. So it's straightforward for NORAD-SAM developers to use, because we are all kind of running this model together. So we had to have like a common workflow. Yeah, and the code is on GitHub. And if you have questions, you can ask here, or you can also contact me. Yes.
Any questions for Ada?
Hi, Ada. Nice talk.
Hi.
On the last slide you showed with the time series of the fully coupled with the different parameter sets, two of the experiments, the long wave cloud forcing changed a whole bunch. I can't remember if it went down by like 5 watts, but what parameters did you find that were so strongly important for changing the global long wave cloud forcing?
Yeah, that was this, it's from the micro physics, this VTRMI factor. So it scales the ice and snowfall speed.
Gotcha. Okay, so that was pretty much the thing that was branching the two different long wave cloud forcing extremes, was that fall velocity parameter. Thanks. Okay. Actually, one more question, since apparently we have some time. I'm curious what like kind of throughput you're getting with this 2-degree model and like in core hours per simulated year. You know, ours is about 6,000, so I'm just curious.
Yeah, so now we have some problems with the 1 degree, so that we can only run like 8 years at a time because we have a memory leak. So that's also coming into here. Then we have to resubmit. So this one we can run as long as we want. We don't run into that problem, but the throughput is 18 years a day. But I should remember the cost. I think it's like 2,500 to 3,000 approximately. Yeah.
I'm curious if you've compared your 2-degree PPA with some of the earlier 1-degree PPEs that we've done here at NCAR to see if the parameter sensitivity is comparable.
Yeah, so we took this, we chose the parameters and also the range through this paper. But we haven't, I know Ben Sanderson, he's also working with NordSM, so he has done some actually analyzed the data. But we should compare that, absolutely. We haven't done that yet.
It would be nice to do PPEs at 2 degrees and not 1 degree.
Yeah, I agree.
Okay, let's thank Ada again.
Thank you.
Okay, next up is Wei-Liang Li. I don't know if it's online. No, you're right here. Yeah, sorry about that. You have all the time in the world here. You have until 3 p.m.
That's good.
I'm just going to talk about the development of high-resolution Taiwan Earth system model.
Sorry. So this one is okay. Back. Okay, so thank you for this opportunity to give a talk here. As you may already also know that we got in Taiwan we got a funding cut from our government. So in the last time I got collect enough funding to come here. So yeah, and today I'm going to talk about the development of the Taiwan Earth system model in high resolution, and this is our list of our team, and yeah, then. So our CESM is based on the CESM 1.2 with only some modification because we have only very limited manpower. And so in the atmosphere part, we add a trigger function for deconvection. Basically, this is borrowed from NOAA global forecast system. And then we change the cloud fraction parameterization. We call it GTS. And then we use a locally developed aerosol scheme, which is a prognostic 3-moment aerosol scheme, consider not only the number and also the mass and also the surface area. And also, we modify the land model to consider the three-dimensional interactions between radiation and topography to consider the effect of the shadow and the reflection between topography. So, our goal is to improve the ability to simulate the climate variability in the spatial and also temporal scale. So there's some features of CESM that meet our goal to improve the simulation of variability. For example, the monsoon rainfall in 4 major monsoon regions, such as Africa, South Asia, East Asia, and Central America. And these numbers are CMIT models, and the CESM is red cross, and the ensemble mean is orange cross. You can see that in most regions, CESM performs quite well, particularly over the East Asia, which is surprising for us and meet our goal. So, and then we can consider the extreme precipitation in East Asia for the May season, which is in the spring, and also the typhoon season in the summer. As we can see that the also for the indexes of extreme precipitation, CESM performance is also quite well. And also for the most of the tropical regions, the precipitation extremes also perform pretty well. So it's basically it's meet our goal, although we don't really know why. But we think the CESM1 is quite good for simulate the extreme event, such as it has the potential to simulate them, such as typhoon or monsoon or frontal systems. So therefore, we would like to, based on this CESM1, to do a high resolution simulation to see how it works out. And then so we carry out several experiments. First is the of course, it's a standard low resolution CESM1, which is 100 kilometer for atmosphere and ocean. And also carry out a prescribed SST for high resolution atmosphere using 25 kilometer atmosphere. And also for high resolution couple simulations, we carry out 2 runs. One is the high resolution atmosphere, low resolution ocean. We call it HALO. That is a compromise because although most of the chips are manufactured in Taiwan, but we academic sectors actually cannot afford it because most of the chips are already sold out to the big companies in the United States and, for example, China previously. So we only have very limited computing power, so therefore we try to do such a way that to simulate using a low-cost strategy. So, and the other one is, of course, the high-resolution atmosphere and the ocean, using 25-kilometer atmosphere and a 10-kilometer ocean, and then compared to observation. So the table in the right-hand side shows the global mean of these variables. As we can see that, for example, the surface air temperature, all the simulations are quite close to observation. And also for the type of atmosphere radiative budget residual, it is also quite close to observation with a little bit positive value indicating global warming. Although this variable seems quite well, one thing we need to consider that is the cloud forcing is too weak for CESM, particularly for high resolution. As we can see, the shortwave cloud forcing is too weak, and also longwave cloud forcing too weak. Although the total cloud amount is a little bit more than observation. So this is an area require more investigation. And so first of all, we'd like to see the SST deviation from observation. So this is observation, Hadley SST, and also high resolution HALO and HALO. So we can see that in high resolution difference, we can see, first maybe you can see that the HALO minus Hadley SST, the temperature is a little bit lower than observation, particularly over the North Pacific, but it's and also colder in the North Atlantic, but in the Southern Pacific, it's basically warming. And for HALO, this the deviation is significantly smaller, as we can see that warming in the Northern Hemisphere, quite remarkable. And they will affect the phenomena that we will show later. So yeah, in the North Pacific, and also we can see that in the Khotan regions, although the high resolution ocean does not necessarily perform better in this region. We still don't know why. Okay, so we focus on the tropical cyclone simulation, and the bottom panel shows the observation IP tracks, and the upper panel is the low resolution CESM. So of course, we know that 100-kilometer resolution cannot resolve tropical cyclone pretty well, so there are very low number of tropical cyclones. When using the high resolution atmosphere model, we see that the number is quite comparable to the observation, although in the Northwestern Pacific, the region that we focused, because Taiwan is here, so the number is still too low, and we have too many TC in the Eastern Pacific. And when we use the HALO configuration, we found that, okay, right now the Northwestern Pacific has pretty well performance, and also in the Eastern North Pacific. However, in the Atlantic, most of the TC disappear, particularly for those TCs originate from the coast of Africa. Most TC are only appear in the North Atlantic. And yeah, for the high resolution atmosphere and the high resolution ocean, we see that it's a booming, that in almost everywhere, all the ocean basin, the TC number increased a lot. Okay, so first we would like to investigate that how coupling changes the TC number in the Pacific. As we can see that in the Pacific, this type of panel shows the vertical wind shear. It decreased a lot in the Western Pacific, and yeah, so it favored the generation of TC, and also in the mid-troposphere, specific humidity also shows a similar trend. And the bottom panel shows, I think, is the most important factor, that the warmer sea surface temperature in the maritime continent generate lots of TC, and in contrast, in the Atlantic, the lower sea surface temperature decrease the number of TC generation here. And one other thing noticeable is that the much colder North Pacific suppress the movement of the TC into the Northern Pacific. So it also decreased the number of the genesis in the Eastern Pacific. And then the other thing is more related to the larger scale dynamic pattern that we can see in the AMWG simulation. Can I see here? Okay, in the AMWG simulation, the Pacific high is very strong. It extends all the way from the Pacific to the Philippine Sea that suppress the genesis and also the movement of TC in this region. And in the HALO simulation, we see that Pacific high is more close to, the region of Pacific high is close to the observation, also in a hair-hole simulation. So it allows more TC to genesis here. And also, this panel shows the annual cycle of TC numbers that we focus on Western North Pacific, that here. And for the hair-hole and the halo, they can both simulate pretty well the annual cycle, although the peak occur a little bit late compared to observation. And in the Atlantic, we see that the number of the AMWG run and is close to observation. And also, as we showed before, although the hair-hole simulation has pretty good number compared to observation, its peak is significantly lower. That is compensated by the TC genesis in winter. That is not good. So and also for the TC intensity that we see in the hair-hole simulation, we create lots of weak TC in both Northwestern Pacific and the Atlantic Basin. And in the strong TC, the number is very comparable to halo simulations. So we have 2 weak TC in halo and also too many TCs in winter. And it implies that the algorithm for detecting and tracking TCs may require adjustment, not related to the dynamic itself. And one thing we like to turn to the ENSO simulation. This panel shows the standard deviation of SST. The top 2 are observations, and this one is low resolution TISM historical, and this one is halo simulation. We can see that the amplitude of TISM is a little bit stronger than observation. And turns into the high resolution ocean simulation, we see that the variability almost disappear in the equatorial Pacific, which is not good. And also we know that this phenomena also occurs in some other models, such as maybe NORESM or the Australia model. And one thing we also noticed that is the very strong variability in the Northern Pacific out of the Japan region. It is a common feature for TISM, or even in the low resolution version. So this one may result in a very cold bias in the North Pacific, and it requires additional investigation. And then this figure shows the power spectrum of ENSO. Maybe not very clear. Okay, so the top 2 are observation, and this one is low resolution TISM. We can see it's not very clear, sorry about that. Okay, the amplitude of the low resolution TISM is comparable to observation. However, when changed to high resolution atmosphere, the ENSO variability is way too strong. The vertical scale are different from this one to others. So you can see this one is very strong. However, in the high resolution ocean model, the variability is very weak, particularly for higher frequency one, such as 2-year or 3-year peak, almost disappear. And the right-hand side is the wavelet analysis. We can see that these upper 2 are also observation, and this one, low resolution one, performed pretty well, and the high resolution atmosphere is too strong. However, in the high resolution atmosphere and the ocean, it almost disappear. So this is summary that we try to establish the high-resolution atmosphere model using a different resolution of ocean, and it can, using the high-resolution atmosphere model, can reproduce pretty well the TC numbers and the tracks in the Northern Pacific. However, ENSO are too strong in the low resolution ocean model, but almost disappear in the high resolution ocean model. And we still try to figure out why is that. So I will stop here. Thank you.
I didn't think I would be saying this, but thank you for going over time.
Okay. Yeah.
Are there any questions for Wei?
Oh. You only showed like 35 years from the Halo simulations for ENSO, and you said it's too strong, but you could, I mean, the middle period there, I know it's only a few years, it's kind of weak. And do you think you have enough years to say that what you put on your summary slide, that it's too strong? Because the spin up, I mean, you're starting from zero there, what are the trends like at spin up? Because we find that in general
we
you get
take
quite a
20
bit.
years for spin up.
Okay.
And then after 20 years, the TOA balance is almost reached, and also temperature does not have a significant change. So we consider it's already spin up. Yeah.
Could you show your Halo versus HAHO SSTs? Looks like the upwelling is actually stronger in the low resolution model than in the high resolution model. That seems kind of unusual.
Yeah.
Okay.
Yeah, we surprisingly found that. We don't know why, actually.
Okay.
Another ENSO question, nice talk. So is it safe to assume that maybe the higher resolution ocean model, the submesoscale eddies, are reducing ENSO amplitudes in that? Or why do you think you might be having such a weak ENSO with higher resolution?
Actually, we don't have any clue at this moment. And our guessing is that maybe we need to, I'm not quite sure because I'm not familiar with the ocean model. Yeah, but some of our colleagues consider that maybe we need to tune the mixing parameter. Yeah, maybe you will help. We are working on that.
Let's thank Wei again. All right, will we convene at 3:30?
Hello, everybody. Welcome back. By the way, for those of you who don't know me, my name is Hui Wan. I'm at PNNL. I'm one of the external co-chairs of AMWG. In the second half of this session, I will help Peter a little bit with the logistics and introduce the speakers. Our first speaker of this session is going to be Aaron, who is going to talk about aquaplaning simulations and QBO.
All right. Well, thank you, everyone. So today I'll be talking about using an aquaplanet model to understand future changes in the QBO. And so just to refresh your memory, the quasi-biennial oscillation, or the QBO, is an oscillation of the stratospheric zonal winds. And so as you can see, I've kind of highlighted this area in the black box. That's the tropical stratosphere. And so essentially you have descending regions of westerly and easterly zonal winds. And so if you focus on a single pressure level, you'll get an oscillation back and forth between westerlies and easterlies with an average period of 28 months. And so the QBO is driven by a wide spectrum of vertically propagating equatorial waves. So you can kind of see that by these wavy arrows here. So as these waves propagate upwards, they deposit their momentum in the QBO region and cause those zonal jets to descend over time. The descent of the QBO zonal winds can be slowed by the mean meridional Brewer-Dobson circulation, which is shown by these white arrows here. And it's generally upwards in the tropical stratosphere, which is counteracting the QBO. And despite the QBO's importance to the global climate, its response to increased greenhouse gas concentrations is still quite uncertain, especially changes in the QBO period. So considering this disagreement among fully coupled climate models, it can be useful to use an idealized model to improve our understanding of atmospheric processes and to better identify these cause and effect relationships between, for example, a CO2 radiative forcing and then ultimate changes in the QBO. So I've kind of shown a list of climate models in order of increasing model complexity, starting with, on the left here, a dry dynamical core, which would simply use a simplified physics scheme, which is maybe a relaxation towards a prescribed temperature profile. And then where my work fits in here is in the aquaplanet framework, which is the simplest climate model that you can fully model the response of the atmosphere to CO2 radiative forcing. So you have the full radiative transfer model here. But you still have very simplified boundary conditions. So for example, you have no land, as the name suggests, no ice, and also no seasons. And you have a prescribed ocean. And so, of course, we have more complex configurations, such as AMEP here, where you also have a prescribed ocean, but you use the full complexity atmosphere model. And then, of course, a fully coupled model as the most complex. And so this is the first time, as far as I know, that the QBO response to increasing CO2 has been analyzed in such an idealized model. So just to describe this aquaplanet model a little bit more, we're using the community atmosphere model version 7. So this is the most up-to-date version of NCAR's atmosphere model. We're using the spectral element, or SE dynamical core, at a 100 kilometer, roughly 1 degree horizontal spacing. And this is just so that we can adequately resolve the equatorial waves that are important for driving the QBO. We also use a 72 level vertical grid, and this provides sufficient vertical spacing in the stratosphere to resolve equatorial wave breaking. One of the reasons why we're using this latest version is because it incorporates a fix to the convective gravity wave scheme. So these parametrized waves are very important for driving the QBO in models with large horizontal resolution. And then we remove aerosol radiation and aerosol cloud interactions just to simplify the model, and ultimately they don't contribute much to the QBO. And so all greenhouse gas concentrations in this model are fixed except for ozone, which has this profile shown here on the right. And so briefly, the experimental setup is, of course, a control simulation, which I call 1 times CO2, which just uses the default aquaplanet experiment CO2 concentration of 348 ppmv. And then that configuration uses the QOBS sea surface temperature profile shown on the right here as this solid line. And that's really just meant to mimic annual average sea surface temperatures on Earth. And we also have a quadrupled CO2 experiment called 4 times CO2. And then the 4 CO2 4K experiment, where in addition to quadrupling CO2, we add a positive 4 Kelvin offset to the sea surface temperature, as shown by this black dashed line here. And this is really to incorporate an ocean feedback to our idealized climate experiment. So to get into the results a little bit, these are difference plots between, on the left here, the 4 CO2 experiment and the control simulation. And then on the right, these are difference plots between the 4 CO2 4K simulation and the control run. And if we look in this bottom row here, these are temperature differences. And we see that in both elevated CO2 runs, we have stratospheric cooling. And so this is an effect of the direct radiative impact of CO2, where we have greater long wave emission cooling the stratosphere. But interestingly, we only have tropospheric warming in this 4 CO2 4K simulation, and that's connected with our increased sea surface temperatures. And then we also have some changes in the zonal wind patterns, which are seen also in fully coupled models in climate change. Now, just to specifically talk about the QBO, what I've plotted here is tropical average zonal mean zonal wind. And so you can see the oscillations back and forth between westerly winds in the red shading and easterly winds in the blue shading that characterize the QBO. And so if you look at this bottom plot here, this is for 4 CO2 4K. And we actually see a shorter QBO period by about 10 months, and also a slight decrease in the QBO amplitude, especially in the lower stratosphere. And since this is the case where we see the largest change in the characteristics of the QBO, this is what I'll focus on for this talk. And so, of course, we want to understand why the QBO is changing in response to our increased CO2 and sea surface temperatures. And we can do that using what's called the Transformed Eulerian Mean, or TEM framework. This is essentially just a zonal averaging of the equations of motion with this additional transformation shown here to the mean meridional and vertical pressure velocities, giving us the so-called residual velocities. And this zonal mean framework is useful because the stratospheric circulation is essentially a result of the interaction of small perturbations in the longitudinal direction, or waves, with a largely zonal mean stratospheric flow. So think, for example, of the Brewer-Dobson circulation I was talking about earlier. And so in this formulation, we have a TEM zonal momentum equation. On the left here is the time tendency of the zonal wind, which we use as a proxy for the QBO. And then, of course, on the right, we have various different driving terms. The first of which is due to advection by the residual circulation. So this is, for example, how the Brewer-Dobson circulation would influence the QBO. And next we have contribution from resolved waves in the model called the Eliason-Palm flux divergence, or EPFD. We have a contribution from parametrized gravity waves. And then finally, a leftover term, which in climate models is usually due to numerical diffusion. Here this term is small, so I won't focus on it. And so, of course, we can plot all of these terms in the QBO region. And so I've done that here just for the total tendency and the resolved wave tendency, or EPFD, specifically for the descending westerly phase of the QBO. So you can see by this solid purple line here, we have westerly winds overlying easterly winds centered at 20 hectopascal. And in this rightmost panel here, we have a difference plot between 4CO2 4K and the control simulation. And we see that we have an increase in the zonal wind tendency, largely due to this resolved wave forcing. And since this increase in tendency is located below the core of the westerly jet, that means that resolved wave forcing is actually will hasten the descent of the westerlies and shorten the QBO period. We can also look at the parametrized wave forcing. Again, another difference plot over here, this time in the descending easterly phase of the QBO. And we see once again that this tendency increases in magnitude. So this easterly jet will descend more quickly and the QBO period will decrease. And so I wanted to kind of figure out why we were seeing this change in gravity wave momentum flux. Usually it's due to a more intense tropical convection, but actually in this case we didn't see very much change at all in the intensity of tropical precipitation. So what I think is causing it instead is this change in tropical tropospheric westerlies, so we have much stronger westerlies. And the mean wind within the convective heating region is actually a very important parameter for generating these gravity waves. So I think that since we're changing that parameter here, we're getting this additional asymmetry in gravity wave momentum flux that's increasing the gravity wave tendency aloft in the QBO region. And then so I also mentioned that we have a decrease in the QBO amplitude. You can see that on the right here, especially in the lower stratosphere. And so this is associated with increase in tropical upwelling as shown in this left panel here. And this is sort of a well-documented result of increased tropical upwelling that also we see in comprehensive climate models. And essentially the buffer zone, which is where the QBO dissipates despite sufficient wave forcing, the depth of that region is really controlled by the strength of the tropical upwelling. Since we have stronger upwelling here, that zone expands and we see a decrease in QBO amplitude. So just to summarize the points I've made so far, we see that the aquaplanet QBO response qualitatively agrees with comprehensive climate models such as in CMIP 5 or 6 or in the QBO initiative experiments. Namely, when we increase SSTs and carbon dioxide and 4CO2 4K, we get a shorter QBO period. And this is a result of increased wave momentum flux. The one inconsistency which I mentioned is that the increased gravity wave driving doesn't seem to be a result, at least, of more intense convection, but rather of these increased tropical westerlies. And then we also see a decrease in QBO amplitude for the 4CO2 4K simulation as a response to this increased tropical upwelling. So that's all I have, and I'd be happy to take some questions.
Questions from the room?
Yeah.
How well does the AM7 and the QBO
Yeah, so actually in the aquaplanet simulation that I'm using, you prescribe sea surface temperature. So there's actually, you're not including any of those teleconnections. So for example, you wouldn't get the QBO MJO teleconnection because there actually is no MJO in an aquaplanet. So really in this study, we're just examining the QBO response to CO2 without really considering any of those complex teleconnections.
Seems like I didn't see any impact of the CO2, and it seemed like it was the plus 4K that made the difference. Is that your conclusion? And
yes, exactly, yeah.
Is that what's been seen before in full GCMs?
Yeah, I think so, because really it's these tropospheric generated waves that are driving the QBO. So it's much less the in situ radiative perturbation from CO2 that's impacting the QBO, but rather tropospheric changes and the response to tropospheric warming that are important.
There are no further questions. Right now, let's move on to the next presentation.
Thank you.
Next, we will have Christiana Yapnonovsky talking about insights from the most recent DCMIP summer school.
Yeah, I have the pleasure to tell you about an event that happened actually last week here at NCAR. And this is a dynamical core model intercomparison project, and there are many, many people involved, as you see here from my long list. Just want to highlight, this is a collaborative effort from, I guess, the University of Michigan, where I'm from, led by us, and then together with NCAR, Sandia National Labs, Indiana University. Also, we had a representative from the UK Met Office, actually, with us, and CSU, I should maybe not, I should really mention all, CSU, Don Denslig and Colin Zaziki from Penn State University. All right. So what is DCMIP? Maybe you know it, maybe you're not. So if you haven't heard this acronym, this is the Dynamical Core Model Intercomparison Project, and we have been running this a few times. You see it in my next slide. This time around, we had desired to intercompare 3 dynamical cores that are available in the NCAR framework in CAM, plus the UK Met Office, the newest UK Met Office model, which is called ELFRIC. It is actually a summer school. It's 1 week together with 50 students and about 10 mentors, so about 6. And here you see kind of a photo of the 60 participants, including the mentors that were here at NCAR last week. We focused on idealized test cases and also this time a very new element, which was an idealized test of machine learning emulators, which we had never done before in DCMIP. Right, here you see a little bit of the history of DCMIP. So we actually started this endeavor in 2008 and were on a 4-year cycle. Yeah, you see a little bit of that history here with, for example, Peter Lauritsen, always a partner here. Our plan to do it in 2020 fell through due to COVID, so this was actually now our 2020 version, basically. And it was always an event with a lot of modeling mentors, even from the international community. This time around, we kept it a little bit in-house here at NCAR. All right, let's maybe dive a little bit, and this is a really short talk. I just give you the essence of the test cases and a couple of results, and there's a lot to look at. So I want to point you to the DCMIP webpage. It's a wiki that we created last week. There are many, many diagrams and graphics there if you really want to dive deep. But let's maybe just today focus on the design of the test cases, which we created for this event, and we have basically 3. So let's kind of take a look. So the first 2 are mountain generated, and they are different scales. The first one is kind of looking at inertia gravity waves. The second is mesoscale, where we shrink the Earth to go to so-called gap flows or vortex streets. And the last one is actually a moist one, where we look at physics dynamics interplay at non-hydrostatic scales on a small Earth. And the last one is a little bit independent, which is machine learning. All right. So let's kind of take a look. So scientific motivation for number 1, which is inertial gravity waves, is actually just the presence when you kind of, take a look at our mountain ranges, the presence of these large mountain ranges, and especially let's maybe take a look here, at the Andes. This is a real long mountain range, which we kind of used for inspiration. And when you then basically kind of see this a little bit down here, the mountain range. If you put that into the mid-latitudes, we put it at 45-ish or so. It's a really long ridge. We are watching basically here the gravity waves bubbling up. So in color here you see actually the hydrostatic divergence on top of potential temperature. So the essence of the test case was actually, you see the perspective element model here to intercompare vertical spacing, so 800 meters in the vertical versus you see it here as 200 meters. And the trick here is to really see how much resolution do we need to have a truthful representation of breaking gravity waves. Because gravity waves bubble up in this regime, they should break, they become actually really short, and 800 meters are not capturing them. There will be aliased, spurious numerics will come in, and that's really what we wanted to learn. So this is an example of this, of the first test case. Okay, number 2 has kind of 2 variants, and here you see our kind of scientific motivation. The first one is a so-called gap flow, and this is actually an example from nature. Yeah, this is now a gap between 2 mountains. You see them in Mexico. Typically, we have a northern wind. It's squeezed through the gap, and that's really what we wanted to test, because then it's accelerated, it's partially blocked. The other scientific motivation is this nice-looking von Karman vortex street. You see 2 islands here, Madeira and Gran Canaria, used as motivations, and then you see the swirls, and this was something we wanted to mimic, not with clouds, but with a dry setup. Okay, let's take a look. And those are now the gaps. So you see this mountain, and here you can really play with Coriolis force, without Coriolis force. This is an example. Let me just play one with the spectral element dicore. And in red, you see acceleration. You see actually the flow kind of going through the gap. Let's kind of take a look here. Throwing through the gap, partially blocked here, but really accelerated. And this is without Coriolis force. And yes, you can repeat that with Coriolis force. And when we play that one, it's looking actually quite different. So here the Coriolis force is really making a big difference in the flow field. And this is just, again, it's basically an acceleration. Okay. Let me just move on and go to number 2, which is shedding vortices test case. Again, we could play with and without Coriolis forces here, and you see the mountain, a little bit different shape, Gaussian mountain, all analytic initial conditions, so very, very easy to set up. And if you now play that, and you basically see these shedding signatures, yeah, so you see behind the mountain, so the flow hits the mountain, and this is now a temperature perturbation from the isothermal initial condition, and it's really nicely shaping up into this swirling flow, and it looks kind of like the fun vortex Karman street, and these are really, really easy to set up in dynamical cores. Okay. I think I should just wrap up a little bit. We intercompared different dicores. Here you see that, different dicores do give us different signatures, SE, FE3, and MPAS, and we will need to dive into these a little more in the future to make statements about, what's the true solution. I can't really make a statement right now. Yeah. But of course, we see, sensitivities to diffusion, to resolution, and that will be explored a little more in the future. Okay. This is another depiction from the UK Met Office, from the so-called ELFRIC model. Basically, it's also showing us, these nice swirls, but also at the very end, look at the noise, that's appearing. So this was actually also news to them. So, it's a test case that served its purpose because the UK Met Office learned something about their own model. All right. Let's go to number 3, and then I kind of wrap up. Number 3 is now a moist test case. This is really mimicking a squall line, but with idealized initial conditions. You see a little bit of this setup here. Oops. So setup is like, low-level wind shear, no shear in the upper domain. This is zonal wind. And the squall line gets triggered by bubbles. Yeah? So you have here 9 bubbles or 7 bubbles, 1 bubbles, and they trigger convection. And that's really the essence of this test case. Here you see a little bit of that. We run this on a really small planet, the 2-kilometer grid spacing. It's non-hydrostatic. And you see now kind of the progression, 30 minutes in, an hour in, 90 minutes, and so on. After 3 hours, we have that nice kind of bow echo form. While the results are all over with different, dicores, that's again to be explored. And here you see a little bit of that. Yeah, so here you see a comparison between, the SE. Let me point it out, the SE, FE3, and MPAS dynamic core. This is radar reflectivity, a measure that we put as a diagnostic into the model. to evaluate that signature. Okay, I probably should wrap up. Last but not least, let's kind of take a very quick look at machine learning. And this is very exploratory, but I think something to come in the future. And here we used something from NVIDIA. It's called Earth-to-MIP. It's basically a framework for different emulators. And they included, the emulator included were GraphCast, ForecastNet, and also Panju Weather. These are 3 emulators from the community. And we used them out of sample a little bit. For example, and I only give you one example, they are trained with ERA 5, full complexity, seasonal cycle, diurnal cycle, everything, topography, and we gave it a really idealized initial condition, which wasn't in the training data set. And we wanted to see whether a steady state would be a steady state, which it would be in a DICOR, and of course it isn't. Yeah, when you give it to a machine learning emulator, that's probably expected. And here's some proof of it. So we should see a steady state. There's no steady state, as you see. We see a couple of different variables, 2-meter temperature. This is water vapor, 10-meter wind, and mean sea level pressure. It's looping, yeah, so initially it's a steady state, or it's very zonal, but immediately you see the flickering from the topography. You see a seasonal, not seasonal cycle, but diurnal cycle. So yes, this is actually learned by the model. Maybe that was expected, but we are following up with a couple of new ideas, actually, how to really test physical consistency of emulators. That's the approach we want to use in the future. All right, let's just kind of close here. This was really a quick preview or overview of DCMIP. Again, we looked at a variety of dynamical cores with idealized test cases. We use this as a research tool for ourselves to learn more about DICORs, but also it was an educational event with 50 students that we trained on model development, and it was hands-on. It was very lively. And the future maybe goes a little bit more into the machine learning world, but that's to be seen. So, yeah, thank you. That's my last slide.
Rosanna, we could perhaps accommodate one short question. If not, then let's move on. Let's move on to the next presenter. Then Luan will be talking about QBO, gravity wave, and deep convection responses to surface warming in GFDL's AM5.
Hello, everyone. I appreciate having the opportunity to talk about our research at the CESM workshop. I would like to thank my collaborators, and thanks to Pooh, we have all the simulations. She did the AM5 simulations, and my work is based on those simulations and looking at the QBO gravity wave, deep convection responses to surface warming in GFDL AM5 simulations.
Move your mic a little closer.
Okay.
Oh, pardon mic. Thank you.
The motivation for our work is there is no QBO in earlier version of the GFDL model, AM4. If you look at the middle panel, you could barely see the QBO signal, and there's only like a seasonal cycle in the earlier version compared to the ERA5 reanalysis. The earlier version of the GFDL model uses the AD99 gravity wave parameterization scheme, and in the ongoing developing version of the GFDL model, we use the Bayer scheme, and you could see that at the bottom panel, the QBO signal is more realistic compared to the earlier version. And there are several important factors for parameters for the Bayer scheme. The first important parameter is the maximum heating within the deep plume. It's called Q0. From the model outputs, we only have the great mean heating is the Q. In order to know the maximum heating within that convective plume, we need to divide it by the convective fraction. And in the CAM model, the convective fraction is set to 0.05, and in the vacuum model, it's also 0.05. And in the AM5 model, the tuned fixed case has the convective fraction set to 0.1, and we also have additional simulations use the prognostic updraft area. And another important parameter for the Bayer scheme is the heating depth within that convective plume. And based on the momentum flux equation, we could notice that the momentum flux is proportional to the maximum heating squared. And based on the lookup table, which is based on the heating depth and the average wind within that heating layer, which is a function of the phase speed. And after applying this tuning parameter, we can get the source momentum flux in the AM5 model. And for our AM5 simulations, we have two groups of simulations. The first group is based on the present day simulation. It's the 2010 climatology. And the second group is the increased 4K SST simulation. And for each group, we have 3 sets of simulation. The first simulation, we have the fixed convective fraction. And for the second and third experiment, we have the prognostic updraft area. And we could see that from the QBO period, it gets shorter for the increased 4K SST simulations compared to the present day simulation. And the largest difference appears in the fixed convective area simulation. And for the bottom, we have like a description of the convective parameter scheme that we used in this model. It uses a finite volume coulomb sphere dynamical core, and the subgrade convection is represented by 2 bulk plumes for shallow and deep convection. And detailed discussion about the convection parameter precision scheme can be found in Zhao et al. 2018. And here, showing the zonal mean wind average within 10 degrees north to south. And the panels 1, 3, and 5 are for the present day simulation. And the panels 2, 4, and 6 are for the 4K SST simulation. And you could see that this QBO signal, the period of QBO gets shorter for the future 4K SST simulation compared to a present day simulation. And the largest difference appears in the fixed convective fraction simulation. And the shortest QBO period appears in the panel B, that for the fixed convective fraction case. And the heating depth is an important parameter in the Bayer scheme. And by looking at the present day and 4K SST simulation, the dashed line are indicating the tropopause height. We could see there is an increasing of the tropopause when SST increases. And the black line is the trim observation. And by comparing to the trim observation, we have similar heating depths, except the model have more deepest heating depth cases than the observation. And another important factor in the Bayer scheme is max heating rate. The solid lines are for the present day simulation, and the dashed line are for the 4K SST simulation. The black line is the trim observation. And we could see that there is more strong convection in the when we increase the SST compared to the current climatology. And trim have larger maxi heating rate cases compared to the present day simulations. And we could notice that the maximum heating rate is positive correlated with the QBO period. When we have stronger heating, the QBO period gets shorter. And we also have this 2D PDF showing the distribution of heating depth and maxi Q. And the left panel shows the trim observation, and the red panels are for the simulation we have in the AM5 model. And from this plot, we can notice that the maximum heating rate and the heating depths are positively correlated. If you look at the yellowish color is where most cases happen. So this is a log scale plot. The yellowish color means there's more cases than the other, like the bluish color. And for prognostic convective fraction simulations, the distribution shows wider range at lower, shallower heating depths. And that means this region have wider distribution. And next, we did an offline Bayer scheme calculation looking at 100 hectopascal gravity wave zonal momentum flux phase speed spectrum. And what we see here is the 4K SST simulation show a broader phase speed spectrum and more momentum flux than the present day simulation, and this leads to a shorter QBO period. And the fixed convective area simulation shows a larger change in the phase speed and the momentum flux comparing to the prognostic convective area simulations. Here comes the summary. The number of extreme deep convection events increases with the increasing SST simulation. It leads to more gravity wave momentum flux and a broader phase speed spectrum, and thus a shorter QBO period. The prognostic convective area introduced less strengthening and broadening of the phase speed spectrum for the 4K SST simulation, and it leads to a smaller change in the QBO period compared to the fixed convective area simulation. Yeah. Thank you. I will take any questions.
In the microphone.
Is the lesser change in the 4K SST simulation for prognostic cloud fraction simulation is because are there some compensation from the increasing cloud fraction to cancel out the increase in Q naught? Were there?
Yeah, do you mean why there's a larger change in the fixed convective area case than the prognostic? Yeah, that's a good question. For the fixed case, we only use 0.1, but for the prognostic convective area, it has so for the fixed convective area simulations, it have larger maxi Q, and that's one point. And for the prognostic simulation, it doesn't. I look at the distribution of the convective area; it doesn't change a lot. So the larger change is in the heating rate.
Cloud fraction rate.
Yeah.
You again, and so in the interest of time, let's move on to the next presentation, which is a Earthworks update from Dave Randall.
Okay, you see the long list of names here. This is a joint project between CSU and NCAR. And I want to particularly call out the important contributions from Brian Dobbins, who's listed on the third line here. And I'll mention him again a little bit later. CGD generally has been very supportive. So we've been doing releases for a few years now, and we're just released 2.5. And this brings us up to date with CESM 3-0-beta 06, which means that we're contemporaneous with the developmental version of CESM. And this brings in a lot of optimizations that were developed for the diamond runs, which I'm going to talk about. We have in this new release better support for the MPAS ocean and sea ice, which were developed at the Los Alamos National Lab. And I'll show you some results from that here in a few minutes as well. We also have the same kind of support for finer grids. And there, it says fixes several software issues, fixes a lot of software issues, some of which are still pending. So one of them, I won't spend much time on the slide, but you know, there are various software issues with the model itself. And then there are software issues that relate to the infrastructure that we use from outside, in particular the compilers. And we've had some trouble with the NVIDIA compiler recently. And it turns out that these issues have been due partly to the way the code is written, not just in one place, but in many places throughout the model, but also partly due to issues with the NVIDIA compiler. So we've made good progress with this, but it's not completely resolved yet. We've also made quite a bit of progress with the GPU components of the model. So we have the microphysics, that's Puma/MG3, running on GPUs. We have the radiation code running on GPUs, and we have Club running on GPUs. And there's been a lot of work involved here to make this work, to make this happen. And these are now optionally available in the standard CAM as well as in Earthworks. We also have both the atmosphere and ocean dynamical cores running on GPUs. They're both MPAS, of course, MPAS atmosphere and MPAS ocean. For the atmosphere, we're only running on GPUs with simple physics, and that's only available through the Earthworks repository. The MPAS ocean GPU version will be made available in our next release, but it's running now. So we've done 1.5 diamond simulations. This is the intercomparison, the international intercomparison organized by a long list of people, including Bjorn Stevens and Masaki Sato. And here again, Brian Dobbins has been absolutely key to making this go. A lot of difficult software issues had to be overcome to make this possible. So we ran it with CAM physics with a little bit of tuning. And there were also a number of scalability fixes, which means fixes that allowed us to use a larger grid from both ESMF and PIO, which is an I/O package the model uses. And also memory usage has been reduced. So these things led to improvements in efficiency, and in fact, the code actually runs more than 2.5 times faster than we thought it was going to, because we're using longer time steps. We don't have to restart as frequently, and we are using less memory, which means we can use more cores. And further improvements are in the works. In particular, there's an issue with the land surface model, CLM. It uses a lot of memory on startup. It should be using much less, and that problem will be fixed in the coming weeks, I hope. We've also done recently a coupled simulation with the 15-kilometer grid. So the spin-up of the ocean is described here in the top part of the slide. We're following the OMIP protocol. And so we started with a 295-year spin-up on a 120-kilometer grid, driven by a data atmosphere, of course. And then 118 years on a 60-kilometer grid after interpolation. The middle part of the slide tells what was interpolated. And then down to a 30-kilometer grid, we ran 1 year there, and then to a 15-kilometer grid, 2 more months of spin-up, and then we started the model on March 1. And ran for 1 simulated year. So here's a snapshot of OLR. And this has been, this figure was produced using heel picks. This was done for the kilometer scale hackathon that happened a couple of weeks ago. Don Daslick did this figure. So the heel pick zoom level is 9, which corresponds to roughly 12 kilometers, a little bit finer than the actual simulation. And you can obviously see quite a bit of detail here. Here's an animation of the ocean circulation. This is supposed to loop, but it doesn't, at least not in PowerPoint. It looped in Keynote. So that's running fine. And here are some slides that show a particular tropical storm over the Atlantic. You can see the geometry in the bottom left panel there. You can see Africa and North America on the left. So the low in terms of sea level pressure is that little bluish green spot at about 32 degrees north and 300 east longitude in the top left panel. And then you see the wind speed, sort of bright red spot on the right there top, and then surface temperature. Here you can see the wake of the storm. So this is showing that we are in fact using a coupled model. And the OLR then is shown in the bottom right panel, and you can see a spirally shape, looks like a TC. So conclusions, we're doing real simulations now that are of the sort that we plan to do from the beginning. So I'm going to claim that we're in production mode. It doesn't mean that we're finished fixing problems and making optimizations, but we've reached the point where we can actually use the model. We've completed a Diamond 1 run for summer, and we've done part of a winter. It hasn't been finished yet. We may go back and redo it with a slightly different physics. We've also done the 1-year coupled simulation that I showed you on the 15-kilometer grid, and that was submitted to the hackathon, so a bunch of people got to play with it. And we're hoping to do a Diamond 2 simulation in the not-too-distant future. So that could be a 1-year run. And we're working on further code improvements and optimization. And I will say, since the beginning of this project, you know, we wrote the proposal in 2019, and I had no idea at the time how much software problems would, how much work would go into fixing them. So it's been educational for me. That is the last slide.
Dave, any questions? Thank you again, Dave. So the next presentation is going to be given by Timothy Andrews, who will be talking about linear stability of divergence and vorticity damping.
Cool, thank you. So this is work with Christiana at the University of Michigan. So I'll be looking at diffusion in dynamical cores, and specifically looking at stability on cube-sphere grids. So numerical diffusion is a key part of all dynamical cores for atmospheric modeling. So it's present in the model whether it is implicit or explicit. So implicit diffusion can be from time-stepping methods, or maybe your transport scheme. Or you might apply it explicitly through additional terms in your equations, such as your horizontal momentum equation. So there are a couple of key features when you apply diffusion explicitly. So the first is that there is a range of stability for your coefficients. So I'll just call these C for the moment. So there are two factors to this. Firstly, if your diffusion coefficient is too small, then you can have instability because you're not damping the small scales enough. However, on the other hand, if you make your coefficient too large, you can actually introduce stability from the diffusion itself. And it's the second feature that we'll look at in this talk and do stability analysis to get some bounds for this coefficient. So firstly, just describe what divergence and vorticity damping are, what the cube sphere is, and then show some application of CAM FE3. So this is the finite volume cube sphere grid that's used within the CAM model. So explicit diffusion, so if we consider this for the horizontal momentum equations, you can apply this to your horizontal velocity through either a Laplacian term or some higher order operator, which we call a hyperviscosity. Conversely, if you look at divergence and vorticity damping, you instead apply this directly to D, your divergence, or your horizontal vorticity. And doing this means that you directly damp the divergent and vorticity modes. And a key benefit of doing it this way is you can specifically damp either the rotation or the divergence in your model. So we're looking at this on cube-sphere grids. So these have been becoming ever more popular to avoid the pole problem on long lat grids. And specifically the mnemonic version of this is where you take a cube and you project lines from the faces of this cube onto the sphere. So there are three different cube-sphere grids that I like to look at. So the first was the equidistant grid, where basically each of these cube faces was split into equal areas. But the issue with this is if you project it onto the sphere, you get quite a range of cell areas. So the equiangular cube-square grid is probably the most common. So this is used in CAMSE and also by the UK Met Office. And this is where you define equal areas on the sphere itself. Now there's a third grid that's actually special to FV3, and it's the default in CAMFV3. And this is where the cells along the panel edges are made slightly more regular. And this reduces grid imprinting, which can introduce errors during transport. So just to summarize these three grids, so the equiangular one used by CAMSE has the smallest range of cell areas. The equi-edge has a slightly larger range, but the benefit is that we have the smaller aspect ratio, if I can, and specifically more uniform cells at the panel edges. So moving forward, I'll look at the equiangular and the equi-edge grids, and recalling that equi-edge is the default for CAMFE3. Another key point between these two grids is actually the smallest cell is in a different location. So for the equiangular grid, it's in the middle of the panel edges here, whereas for equi-edge, it's at the cell corners. And this will play into the stability of these two different grids. Okay, so let's get to some linear stability analysis. I won't show any of the derivations for the sake of time, but you can see more in our preprint. So here I'm plotting amplification factors to show the effect applying the stability, the diffusion. So here on the y-axis, we're plotting the amplification factor. So if this is between 1 and -1, we're in a stable regime. If this factor drops below -1, then we have amplification from the diffusion, and our simulation will blow up. So thankfully, if we plot the defaults for CAMFE3 on the equi-edge grid, so these are default diffusion coefficients of 0.15, we see that we're in the stable regime for all wave numbers plotted along the x-axis. So here we go, none of these drop below -1, so the defaults in CAM are all stable. But the thing I want to highlight is then I looked at the equiangular grid, which you can switch on in CAMFE3. And in fact, for 6th and 8th order divergence damping, the default coefficient of 0.15 is unstable. So the take-home message here is if you're playing around and want to try a different cube-sphere grid, you'll need to reduce your divergence damping coefficient. Otherwise, you'll cause instability from this. The reason for this difference is that the equiangular grid has the smallest cell at the middle of the edges, and this is the place where the instability forms. And this actually leads to a stricter coefficient bound on the coefficient than on the equi-edge grid. Yeah, I won't go into more for the sake of time. So then I looked at testing these derived coefficients in CAMFE3. So just looking at the baroclinic wave test, running this for 15 days, and basically seeing what was the largest value of divergence damping I could use before things blew up, and comparing the equiangular and equi-edge grids. So in CAMFE3, the diffusion terms that we're interested in are shown here. So here are horizontal momentum equations. We have transport operators, which actually have some diffusion in them. We have vorticity damping terms here, and then we have divergence damping, which I'll look at first. So comparing this, the theory to practice in CAMFE3, I found very similar values, so this was good. And as expected, equi-edge could use stronger divergence damping before blow up. And again, just reiterating that the equiangular 6th and 8th order divergence damping is unstable with the CAM default coefficient. This is, of course, because it's tuned for the equi-edge grid. Just to show that we have blow up in different locations, if you recall, for equiangular, the smallest cell is at the middle of panel edges, and for equi-edge, it's at the middle of the corners. And if we run baroclinic wave simulations with unstable values and plot vertical velocity, we can see different locations for blow up. And as expected on the equi-edge grid, is at these panel corners, and for the equiangular grid, it's at the center of these panel edges. And this is a value just above the stability range to just show that, again, if you are slightly over this, you will cause a blow up of your simulation. So something to be aware of if you're playing around with diffusion. So just briefly go over vorticity damping. So something interesting in CAM FE3 is that the transport operators already diffuse vorticity. And so this means that your explicit diffusion is applied on top of this implicit diffusion. And so you can't nearly have as large values as you can for divergence damping. And we saw this in playing around with some results. And in this case, we got that you could only apply about half the theoretical value of vorticity damping before you got blow up. And so the rest of that was from implicit diffusion of the vorticity. I found interestingly that a higher order of vorticity damping actually meant I couldn't make the coefficient as large. Okay, sorry, no, the other way around. Sorry, I could apply a larger coefficient with a higher order, which is counterintuitive from linear stability theory, something I still need to look at. And the last point is that I applied a number of different transport schemes. So we have monotonic ones, which is we have more constraints and are generally more diffusive, and unlimited schemes with fewer constraints. And there were different levels of vorticity damping I could apply before blow up. And my theory from this is that we can actually back estimate the amount of implicit diffusion in the transport scheme by seeing how much vorticity damping we can use, because there's that play between the implicit and the explicit vorticity damping. So this is something I want to look at further. Okay, just to summarize, so I looked at divergence and vorticity damping on the cube sphere, derived some coefficients, upper bounds to the coefficient, found that on the equi-edge grid, which is the default in CAM FE3, you can use stronger divergence damping than equiangular. And that remember the CAM FE3 defaults are unstable for equiangular if you're wanting to play around with that. There were different locations of blow up for the two different grids, corresponding to the different locations of the smaller cell area. And with vorticity damping, there are differences depending on your transport scheme, and my theory is that this can provide some intuition around the level of implicit diffusion of that scheme. Thank you, and I'll take any questions.
Any questions for Timothy? If so, please come to the microphone.
Were you using the same time step for all of the simulations you did? Because it seems like that could be an issue as well.
Yeah, that's right. I fixed the time step. And in fact, the diffusion coefficients scale with the time step as well.
Okay, thank you again, Timothy. Let's move on to the next presentation. The title is Deep Atmosphere Dynamics in Aquaplanets and E3SM CESM Intercomparison by Owen Hughes.
All right, just as a preamble, there's a bunch of model development work that I don't have time to get into here. I love talking about that offline, and if you'd like to talk about it, I'm always down. So, without further ado, the Intertropical Convergence Zone, or ITCZ, is among the features of equatorial climatology, including the Madden-Julian oscillation, that have had long-standing biases in Earth system model simulations. And the work that I'm talking about today originated in the Department of Energy's E3SM atmosphere model, where in the second version of their model, they introduced a new version of the dynamical core. The dynamical core solves the resolved fluid motion. And this new version of their dynamical core solves the non-hydrostatic equations of motion and is more suitable for high-resolution simulations. the non-hydrostatic home dynamical core. It's sort of a sister die core to CAM-SE, and it's being reintroduced into CAM and CESM as part of the storm speed project. So what I'm talking about today is basically results from E3SM and CESM. So you can ask, do higher resolution simulations resolve the ITCC bias? If you simulate with a non-hydrostatic die core, does it fix it automatically? And what I'm showing here is essentially no. So what I'm showing is 10-year average summer precipitation with a 28-kilometer grid spacing on the, let's see here. So on the left, this is with a hydrostatic dynamical core. On the in the center, that's a non-hydrostatic dynamical core, and on the right, that's a reanalysis product. So what you can see is the precipitation biases are very similar with hydrostatic and non-hydrostatic dynamical core, and so you don't get this for free. But removing 2 additional problematic approximations from the dynamical core are likely going to improve CESM and E3SM's equatorial climatology. So I'll talk about those now. The first one is the shallow atmosphere approximation. Assume that the distance between the center of the Earth and a point in the atmosphere is equal to some nominal value, 6,371 kilometers, for example. And as a consequence, you assume that gravity is constant throughout the atmosphere. But when you make this choice, you also have to make a couple of other things to make angular momentum transport work out. So the metric terms you need to keep a parcel that's not moving radially along a surface changes, and you have to discard those. And basically a parcel moving vertically in the atmosphere, if you're assuming that that radius is constant, the angular momentum looks different if you make that assumption versus not. And so these last 2 metric terms and Coriolis terms are called the traditional approximation. And if you discard the Coriolis terms in the traditional approximation, you end up those are called the non-traditional Coriolis terms. So these 2 approximations are treated as a package deal to maintain angular conservation of angular momentum. So these are what the equations end up looking like, and I can talk about them offline if you'd like. But these 2 approximations are justified for large-scale motion in the mid-latitudes, but in the presence of convective motion near the equator, can we still discard these non-traditional Coriolis terms? Idealized studies indicate no. For example, Hengong's work, who will be speaking after me. And what I want to talk about today are preliminary results from the Deep Atmosphere Home, or SE non-hydrostatic dynamical core in aquaplanets. So we wanted to implement the changes to the die core in the simplest way possible. Home and SE share horizontal numerics, and we wanted to not violate the conservation properties. So we made this list of changes. The main change here is that it's harder to do in a mass-based coordinate model. And I can talk about those details offline. But right now I want to talk about some CESM QPC6 results produced via the storm speed code base. So this is the home or SENH dynamical core with CAM physics. So aquaplanet simulations, remember that you take full complexity atmospheric physics, in our case CAM6, and an idealized ocean, which is a data ocean, no landmass, no topography, no seasonal cycle, idealized sea surface temperature pattern. We're using the control on the right here. And what I want to show is we have an approximate, so on the, let me see here. On the left here, we have the time mean zonal wind in the deep atmosphere model, so this is our new version. Then in the center, it's the time mean zonal wind in the old non-hydrostatic SE. And then on the right, we have the difference. And so this is the difference of the more physically accurate model minus the less physically accurate model. And what we see is basically there is a 2 meter per second bias on top of a 20 meter per second base wind. So by making these approximations, you get a 10% relative error in your zonal wind climatology. And the changes are, you see changes of approximately equal magnitude outside of the tropics. So the linear theory and idealized studies give you a good idea of why the biases in the tropics are happening. Extending this to the mid-latitudes and the poles is going to be a matter of further work. So to return to the ITCZ problem, the QPC6 defaultly shows a double ITCZ, which you can see here in terms of these double off equator peaks. And what you see is that when we introduce the new dynamics, there is more off equator precipitation in the new model than in the old model. And so it actually sort of makes the ITCZ slightly worse, which is opposite to the results that Heng-Ong is going to show with a different die core. So there's something pretty interesting going on here. I made sure, I forced it so that the model would crash if I accidentally ran the shallow case with deep atmosphere dynamics. So I'm sure that I've got the right model here, but more work is needed to say why this is. One other thing, changing gears a little bit, there is a paper from 2005 indicating that the traditional approximation biases tropical cyclone tracks and precipitation patterns. And so an additional simulation I performed was Reed and Jablonowski designed an idealized tropical cyclone initial conditions, and I ran those with aquaplanet physics in quarter-degree grid spacing. And what you find if you run this for 10 days is that the position of the pressure minimum, here I'm showing wind speed, but you can see that the longitudinal axes ranges are the same. And there's about a 2-degree difference in the center of the measured idealized tropical cyclone. And the only difference between these two simulations is the deep atmosphere dynamics. So to compare this to E3SM, we return to the aquaplanet. We've still got a difference in precipitation. So this is time mean precipitation on the left here, deep atmosphere minus shallow atmosphere. And then what you find is that you have a little bit more precipitation around the equator, but it essentially disappears in a zonal average. The physics package that I'm using here is EAMV1 with an E3SM, so that doesn't exhibit a double ITCZ. But you have similar changes in the zonal wind structure, the sort of 10% relative bias that you would expect from linear theory within E3SM. And hang on, we'll talk more about the reasons behind that in a minute. But an interesting result here is that running with a slightly higher model top means that we have 10 meter per second bias in the stratosphere of E3SM. And the reasons for that change aren't super well studied. And further, our immediate future work is going to be looking more at why this is happening. Sort of get these this change in the position of winds with a similar magnitude. So, in summary, we designed a deep atmosphere version of the home dynamical core for E3SM, and we're porting this version into the CAM Storm Speed code base this summer, which will be available to people. And we're starting to look at the systematic biases induced by the shallow atmosphere and traditional approximations in a hierarchy of models. So what we've seen so far is that systematic biases are not just located in the equatorial troposphere. There are stratospheric biases and mid-latitude biases induced by these approximations. And further work is going to be needed to look at, go beyond aquaplanets to AMIP-style simulations, and we're also going to be running some global convection permitting simulations with a 3-kilometer nominal grid spacing this summer to quantitatively look at it on weather timescales. So with that, I will take any questions.
Thank you. So any questions for Owen? So if not, then let's move on to the next presentation. Heng-Ong will be talking about mitigation of the double ITCZ bias by inclusion of the non-traditional Coriolis terms.
Hi. Many thanks to, first of all, and many thanks to NCAR CGD for the travel support. Otherwise, I won't be able to be here. And many thanks to my collaborators, Adam Harrington and Dayang. I borrowed the computational resources from him. And first of all, echoing Owen's presentation, the double ITCZ bias has been a problem in generations of our system models and has been studied for decades, as shown here. This is a paper from 1995, and this project this year. And again, talk about non-traditional Coriolis terms. Most of the global atmospheric models share this common approximation of the traditional shallow atmosphere approximation, which neglects the non-traditional Coriolis terms. And non-traditional Coriolis terms arise from planetary rotation. They turn eastward motion upward and upward motion westward, and vice versa. And from my PhD work, I used this idealized model to study using prescribed heating due to convection and study the flow response to that heating. And I found that omitting the non-traditional Coriolis terms yields a westerly wind bias in an ITCZ-like heating region. And then let's think of what if this westerly wind bias extends into the boundary layer? What happens after that? Well, there would be an enhanced cyclonic vorticity in the off-equatorial region and reduced cyclonic vorticity when we neglect the non-traditional Coriolis term because of vorticity tilting. If we neglect that vorticity tilting, it will have this. So we hypothesize that if we neglect non-traditional Coriolis terms, there will be reduced equatorial precipitation because of that lacking vorticity tilting, which leads to a change in Ekman pumping in the boundary layer. And this is, I first used aquaplanet simulations and switch on and off the non-traditional Coriolis terms in them, and of course considering all the conservations details that Owen just mentioned. And here's the result. This is precipitation climatology with the non-traditional Coriolis term. And this is the difference between them. This is the big difference of precipitation due to neglecting the non-traditional Coriolis term. And as you can see, there is a reduction of precipitation at the equator, and there is an enhanced precipitation in the off-equatorial tropics. And that looks like a double ITCZ, which sounds like double ITCZ may be related to this enhanced off-equatorial precipitation due to neglecting the non-traditional Coriolis terms. And the origin of that, as I just mentioned, it's related to extension of that westerly wind bias due to neglecting the non-traditional Coriolis term into the boundary layer, which changes the Ekman pumping, and then change it. This figure is showing the difference in zonal wind, and this is showing the stream function difference, which transitioning from red to blue in this figure means there is a subsidence at the equator due to neglecting the non-traditional Coriolis terms. So the aquaplanet conclusion is that on the polar side of the ITCZ, when we neglect the non-traditional Coriolis terms, it has enhanced cyclonic vorticity and enhanced Ekman pumping, and thus enhanced precipitation in the off-equatorial, on the polar side of the ITCZ. And the opposite is true on the equatorial side of the ITCZ. Then what we just show is aquaplanet, but it's hard to evaluate because we don't have a real aquaplanet. So next step is AMWG. We want to evaluate our results against observations. So this is the precipitation anomaly observed. And I created this Pacific Equatorial Precipitation Index to study whether the precipitation is concentrated at the equator or distributed into off-equatorial region. And the larger this index, the more distributed the precipitation is to the off-equatorial region. In the observation, this index is 0.24. And this is my, again, precipitation climatology without the non-traditional Coriolis terms. And this index increased to 0.29, which means that the precipitation is more distributed to the off-equatorial tropics when we turn off the non-traditional Coriolis terms. And this is from the simulation with the non-traditional Coriolis terms. And we see that this PEPI index is in between. I mean, it's getting closer to the observation, which means that the inclusion of the non-traditional Coriolis terms leads to a substantial improvement in this index. And we also look at this index in different months, and in most of the months, the inclusion of the non-traditional Coriolis term improves that index, improves the representation of precipitation, whether in terms of whether it is distributed or concentrated toward the equator. And when we look at the zonal mean, first of all, this is showing only results over the Pacific Ocean. And we see that neglecting the non-traditional Coriolis term tends to distribute. If you look at the red dots, which means without non-traditional Coriolis term, and compare that with the blue dashed line, which is with non-traditional Coriolis term, and then compare those with the black line, which is observation, you see that the blue dashed curves are closer to the observation, which means that we are improving the precipitation by including the non-traditional Coriolis terms. And this is zonal mean. Again, we see similar features if we neglect the non-traditional Coriolis term, as we see here in the red dotted line, the precipitation reduces at the equator. And let's see whether it is due to the same reason. We've shown that how non-traditional Coriolis terms influence the zonal wind and the meridional circulation in the aquaplanet simulations. And then if we compare that with our AMIB simulations, which is more realistic, we still see similar features, which showing zonal wind is changed. There's a westerly wind bias due to neglecting the non-traditional Coriolis term over the ITCZ region, and also a subsidence at the equator, showing in both our AMIB simulation and aquaplanet simulations. So here's the conclusion. The climate models have suffered from the double ITCZ bias for decades, and climate models have neglected non-traditional Coriolis terms for decades, with only a few exceptions. And this study suggests that neglecting the non-traditional Coriolis terms tends to distribute the precipitation to the off-equatorial tropics in the aquaplanet and AMIB simulations. And this is due to enhanced Ackermann pumping on the equatorial side, no, the polar side of the ITCZ. And that concludes my talk. Thank you.
Thank you. Any questions?
wondering whether you've looked at something like latent heat flux, because you've kind of, all things being equal, you know, your expectations are what you said, but of course if you're changing the surface winds, you're changing the latent heat flux, and then the cycle kind of adjusts potentially.
You mean latent heat flux?
Surface latent heat flux.
Like surface latent heat flux. Yes, I also see improvement in that regard. So I compare the, latent heat flux. No, actually, I haven't looked at the latent heat flux. I've looked at radiation flux at top of atmosphere and the surface radiation flux, and both also shown improvement when we include the non-traditional Coriolis terms. I look at pattern correlation and RMSE. All those improved when we include the non-traditional Coriolis term.
So if I understand correctly, for your AMAP simulations, there was a marginal improvement in the precipitation, right?
Yes.
So do you think that's not the, exclusion of these entities is not the primary reason for the ICTZ bias?
Maybe not the primary reason, but at least I found that inclusion of the non-traditional Coriolis term can kind of reduce the bias.
For the AMIP-specific simulations, the difference plots look like there were places where maybe the statistical significance of the difference might be in question. Do you plan to run any ensemble stuff to check for statistical significance?
That's a good question. If I have the resources, yes, and if you want to also work on that, we should work on this together.
Yep.
Nice talk. So with the marginal change of precipitation with the non-traditional Coriolis force and without, I mean, like, how much resources you need to run the model with NCT compared to the without NCT?
Good question. There's no difference in computational resource needed when we include non-traditional Coriolis terms. It's including doesn't increase the expense.
Okay, thank you.
These non-traditional terms will be more important at higher resolution since vertical velocity is bigger. I mean, I don't know if there's an area average that you need to account for, but
currently I can only make guesses. Actually, previous studies by Matt Eigel at UC Davis found that including the non-traditional Coriolis term into cloud resolving models also make a difference. And currently I'm using 1 degree resolution, which means most of the precipitation are coming from convection parametrization. And since there is a difference in cloud resolving model due to the inclusion of non-traditional Coriolis term, which may not be represented using convective parametrization, then yes, I would expect if we use higher resolution, it will make a larger difference because of those previous studies, but this needs to be verified.
Any further questions? So if not, then let's thank our speaker again and all the speakers for this session.